Okay, so good morning, everybody. Welcome to the second day of this lovely conference. Thanks to the organizers for inviting me. And what I'm going to talk about is joint work with Marius Krumm, Philippe Allaguerin, and Czeslaw Bruckner. And whoops, what's that? Great. And I'm going to start this talk by briefly reintroducing something which I'm sure you're all familiar with, namely the quantum process framework, and in particular the notion of causal reference frames. Then I will briefly switch to a completely different topic, namely the Page-Wootters formalism, in order to finally tell you how we combined the first two things to get what the title promised, namely the perspectives inside, in general, non-causal processes. Okay, so the process matrix framework was developed to describe something like this. So the idea is that I have agents inside of laboratories where I have a well-defined notion of...
Yes, the screen is not shared. The screen is not shared.
Okay, it's unshared. Okay, good.
Yeah.
So
nothing.
For the Zoom audience, you didn't miss much.
Okay. Very good. And you can minimize the...
Yeah. Okay. Okay, but not good. So, fine. Okay. So the situation we're dealing with are agents inside their laboratories where there is a well-defined notion of local time, according to which at some point the agents receive inputs from their environment, then perform a quantum operation, and then send out an output system to the environment. And then I have multiple such agents. I think this doesn't show the whole thing because there are things showing up there that are not... can I make this? Better? Good. Okay. So I can describe these CP maps the agents are performing on their input system as unitaries if I use a purified picture and give them ancillas. And then the quantum process G is a map that takes these operation unitaries as inputs and produces a map based on those unitaries. And if this G of UA and UB is itself a unitary for all unitary inputs UA, UB, I call G a pure process. And for the rest of this talk, I'm only going to talk about pure quantum processes. And of course, this applies to an arbitrary number of agents, but I'm mostly going to talk about the two-partite case here. Right, as it turns out, such processes G can be incompatible with a global causal order, and we call them non-causal processes, which means that I can not have a well-defined notion of a global time according to which the order of the operations the agents perform is well-defined. Moreover, the pure processes, since they always amount to a unitary transformation, reversibly map a global causal past to a global causal future, but allow for this indefinite causal order in between if they are non-causal processes. So I have something like this. It's again not showing the whole slide, so like this, sorry. In the beginning, I have multiple agents inside their little laboratories and some input state psi. And I can define this notion of global time that just passes from bottom to top. Then there is this potentially non-causal thing in between. But at the end of the day, if I have a pure process describing this situation, all the agents emerge again, and the process G, that is a function of the operations the agents performed, is applied to this input state psi. And at the end, I have again a notion of global time according to which everything moves on in a nice causal fashion. If I now want to talk about perspectives inside such a scenario, I'd rather have a description like this. So the same thing, but now I want to look at a specific agent, labeled X here, according to whose local clock that I drew in these little laboratories, time passes from bottom to top, and at some point, that agent plugs in his or her operation, Ux, into what they perceive as the causal structure of this potentially non-causal process. And the first time the first time somebody looked at such a description or attempted to give one was here in this paper by Philippe and Czaslaw, where they introduced the notion of what they called causal reference frames, which are just decomposition of pure processes that, in case of the two-partite case, look like this. So what they showed is that I can write down a pure process in that fashion, so decompose it into a unitary phi A that depends on UB in general, then in the middle, something where I have only UA and nothing happening to the rest. And then I have this unitary pi A that again depends on B. And this is a way to model Alice's perspective of this process, GUAUB, where that pi A is called the causal past of Alice, and the phi A is the causal future. So I get a picture like this, if you want, perspectival circuit, which is according to which Alice just has her well-defined time when she applies her operation, but in principle, Bob's operation is smeared out across the past and the future. And of course, I can decompose this process according to Bob as well, with now a causal future of Bob that depends on Alice's operation, and a causal past of Bob that also depends on Alice's operation. And of course, for more agents, I have the same thing. So in the middle, whenever I look at the perspective of one agent, I have them applying their unitary in the middle, and the causal past and the causal future that depends on the unitaries of all other agents. And the only requirement in this causal reference framework was that at the end of the day, I get back my overall process GUAUB, but nothing else. So, of course, I can apply this to causal processes, but this is trivial. So if I have a causal process or a higher order map or quantum comb, I have, in the simplest case, something like this, that looks like a circuit but has two slots where the agents can then plug in their operations. And they do this in some order, which is then the causal order of this process. For example, if Alice acts before Bob, I have this here. And then, of course, I can chop up this circuit here into past and future of Alice and past and future of Bob, but this is not particularly interesting. Things are more interesting if I look at non-causal processes. For example, coherent control of causal order. The best known example of which is the quantum switch, which I'm sure almost all of you know. So there I have two operations UA/UB, and depending on the value of a control, my target system either goes through the scenario such that Alice acts before Bob, or Bob acts before Alice, and if I put in an equal superposition of the two, I have a process where I can no longer say that one of the agents acted before the other. And this is a non-causal process and can therefore not be written as a circuit like the one up there. But you can write down two perspectival circuits corresponding to the two causal reference frames inside this quantum switch. on the left-hand side, I have Alice's perspective, where she applies her unitary at some time in the middle. And Bob's perspective is, and Bob's unitary, depending on the control, either gets applied in her causal past or her causal future. And the same for Bob. So in Bob's perspective, he has his well-defined application, but Alice's unitary is, well, in a sense, temporarily delocalized. And you can do something like this for all pure processes. That was the main message of this causal reference frame paper. Good. Now we completely change topic. And I'll give a very superficial and brief introduction of the Page-Wootters formalism, because this is how we chose to model time in what we did afterwards. So the Page-Wootters formalism was designed to incorporate time into quantum theory in a way that is more similar to how I deal with quantum systems, by introducing a clock system and then considering the joint state of the clock and the system I'm actually looking at. So the main idea is that they propose that the physical states, so the ones that are interesting, should satisfy a constraint equation like this. And from this, it was shown that you can recover the standard formulation of quantum theory. In particular, if you choose your clock to be to correspond to, well, have the same Hilbert space as a particle on the real line, and then you pick a constraint operator like this, where the first part acts only on the clock, the second part acts only on the system, and this PT is like the momentum operator. You can write the physical states like this, where this psi of t on the system can be shown to satisfy the standard Schrödinger equation with this Hs from the constraint operator being the Hamiltonian. So, suggestive picture, shamelessly stolen from paper number 6 here, is that via the constraint equation, you get these timeless states, like this block here, but which don't show any evolution. However, if you then look at the clock and condition on a certain time t0, you get a slice out of this. And this slice corresponds to the conditional state of the, well, you call it conditional state. It's the state of the system conditioned on the clock reading that time. And if you then run through all the clock times, you recover a time evolution of the system, of these conditional states. Good. This can also be done for something that we were more interested in, namely quantum circuits. If I have a general circuit like this, where by unitaries U0 to UT get applied, I can also describe this in a Page-Wootters-like way by appending a clock that keeps track of the application of the unitaries. So there I then use a discrete clock system that performs a finite number of ticks. And I can, as shown in these papers here, you can write down a constraint equation and get a physical state that looks like that, where you now, instead of the integral, you have a sum, and the values t run from 0 to your final time big T. And the conditional states of the system are always the unitaries up to point t being applied to the input state phi. And if you condition on the final time, you get your output of the circuit. So we wanted to do something similar, but now looking at multiple clocks. Because we hoped to give each agent a clock, like it is the idea in this quantum process framework, and then recover these perspectival circuits that I briefly introduced in the causal reference frame, from the causal reference frame paper. So Page-Wootters formalism with multiple clocks has been investigated already, last but not least by these people here, like Esteban and Flaminia. But we were now looking at a discrete version, since most of the quantum processes, the whole process matrix framework is more in a quantum info-like language and with circuits and stuff. So we didn't want to look at continuous clocks, but discrete ones. And we were just trying to write down potential physical states that fulfilled, well, the criteria that we deemed reasonable in this scenario, and then looked whether and in which sense they could implement general quantum processes and how they recovered perspectives of agents. Okay, so our physical states live on this combined Hilbert space, where now the HC is not just one clock, but the collection of all the clocks of the agents. HS is just the Hilbert space of the input system. And we also have this H of S bar, which is the space of all the ancillas, which we need for the agent's operations to be described by unitaries. And in general, we get then something like this. So all the clocks should tick from 0 to some final value, big T, although the big T's can be different for the different clocks. And for every collection of clock values, we get a conditional state psi of system and ancillas. Well, what you can immediately say is that we want the first term in the sum to look like this, so all the clocks should read 0. I want the system to be in the global input state phi, or whatever, and then the ancillas, we chose them to be all initiated in some state 0. And if I want to implement a causal or non-causal quantum process now, what I want is that at the end, when all the clocks read their final time, big T, my process G of UA to UN, in principle, has been applied to the input state and the ancillas. And then we said we want to recover the agent's perspective by conditioning on their clock. I will explain this in more detail on the next slide. Moreover, if you remember that I said that the pure processes map this, nice causal past to a nice causal future, we said that, okay, in order to get this picture, we want one synchronized time step of all the clocks in the beginning and at the end. So if I have this, I want now this. So one nice step, which corresponds of all the clocks keeping track of this well-defined global time in the beginning and at the end, and the weird stuff happening in between. Good. Now back to the perspectives. So the perspectives of the agents are given by, at a certain time tx, are given by projecting onto their clock reading time tx. And I need this n x of tx, which is a normalization operator, which you should, for now, just think of a generalization of a normalization constant. It's not, we have requirements on this and motivated in detail in the paper, but for now, just for the purpose of this talk, just regard it as part of a definition that is necessary. Otherwise, with this projection, you end up with something that is not normalized in general. That's why we need it. Good. Then these perspectival states should be unitarily related. So if I'm in a pure process and everything is unitary, I would also want my agent to see a unitary evolution. And we get these perspectival unitaries UX. And now the crucial part, which was motivated by the idea of the causal reference frame, is we require what we call a time of action, T star x for every agent, where if the unitary evolution from the time right before to that time is given by that, the unitary of, the operational unitary, small ux, tensor something that is uncorrelated. In order to recover this idea that at a certain time, the agent just plugs in their unitary into whatever they see, and nothing much else, according to their perspective, happens. So this picture has now become dead. So the agent's local time is tracked by their discrete clock that keeps ticking, and once their clock reads this t star minus 1, they plug in their unitary into the process, and then things keep going, and at the end, they experience this synchronized tick. Good. So this is what we required. Now I'm going to tell you what we got. So this, we found states that fulfilled all these requirements, and indeed could show that they give, well, a refined notion of causal reference frames in the following sense. So if I look at at agent A1 and at the state I get at the end without A1's clock, so after I conditioned on this, I can write it like the lower line here, where you can see that this very much looks like a causal reference frame. So I have a unitary that takes time t0 to t star minus 1. Then at t star, I have this term where the agent applies his or her unitary, and then I have another unitary that goes from t star to big T, and these curly U A1 depend on all the other agents' operations. So I get a causal past of A1, then the thing in the middle where they apply their unitary, and the causal future of A1. And of course, similarly for every agent inside such a process. Moreover, with this incorporation of time, I get some non-trivial perspectives even for causal processes, and I'm going to give an example of that. And most importantly, I get a requirement that we call the fine linearity. Since a decomposition like that exists for all agents, and they all have to relate back to the same physical state, you can show that these perspectival unitaries, which correspond to causal past and causal future, can only be linear or constant in all the agents' operation, which is a requirement that we did not have for causal reference frames, and which is a rather strict requirement. And as I will tell you at the very end, potentially rules out such a description for some pure processes. Okay, first example, which we call the twin paradox circuit. So I have an input state, phi, then that is split between two agents. Then I have agent A applying her unitary, some global unitary in between. Then agent UB applying his unitary, producing this output at the end, which is given by that. But the interesting thing is now that I have time passing differently for the different agents. This is like the twin paradox where one twin moves away at relativistic speed, then comes back, and then finds that the other twin has aged. So Alice moves away, her clock ticks more slowly. Once she's back, Bob's clock is much more advanced than hers. So this is, of course, a causal process with the G of UA and UB just given by this circuit here, looking like that. But what I now get, in addition, is how time runs differently for the different agents. So according to A's clock, we have one time evolution, and according to B, we have another one. I'm going to show you which one. So this is the Page-Wootters state. I don't expect you to remember any details, but just the form of it. So the gray things are the well-synchronized ticks, which you can basically disregard. They are not interesting. And then things happen here in the middle, where the clocks, if you look, so the first part is the clock system where you see that they run at different speeds. So A's clock clearly ticks more slowly than Bob's. So if I then look at the perspective, again, a lot of equations. I'm going to tell you the important bits to remember. Here in Alice's, I get these perspectival states. Beginning and end are not interesting, but in the middle, you can see, well, that's what they look like. But the important thing is that this middle part is where the clocks run at different speed, and this is exactly, these are exactly those states where I have non-trivial normalization operators. So you can see what these normalization operators are good for in that example. So whenever the clock speeds change with respect to one another, you need these normalization operators. That seems to be generally true, and here you have the example of that. If you look at the perspectival unitaries, you can also see what you expect to see. So these T hats are unitaries that make a clock tick once. So this is how Alice sees Bob's clock. And you can see here in the middle, for each time step of her own, she sees 2 time steps of Bob, because you have the T squared. Bob's perspective, on the other hand, looks like this, where you can already read off from his perspectival state that to him the situation seems partially frozen in time. So he sees the same state for 2 readings of his clock, right? And if you look at the perspectival unitaries, you see that he has this time freezes in between, in the part of the, well, his of the story where the clocks actually run at different speeds. Good. So now let's come to some non-causal stuff. In particular, the quantum switch. The G of UA and UB is given by that, where depending on the control, as you see, if the control is 0, Alice acts before Bob. If the control is 1, Bob acts before Alice. You can write this down as an even uglier Page-Wootters state. Again, forget about the details. The important parts are this. So in the beginning and the end, the gray things are, again, the synchronized ticks, which are not interesting. Then the following happens. So this dark green part is where what we call the desynchronization step, where depending on the control, I initiate 2 different clock orderings. So if you see starting from clocks 2-2, I get one term where Alice's clock runs ahead of Bob's, and another term, and the control is 0, and I get another term where Bob's clock runs ahead of Alice's if the control is 1. Then I get this middle part where the agents apply their unitaries, UA and UB. And then I get this light green part, which we call the resynchronization, where I basically undo the different orderings again, for which I have to make use of the control to make the 2 clocks show the same time again, and then do the synchronized step at the end. And I'm not going to write down the perspectival states this time. Again, they are even uglier than for the twin paradox circuit. But you can look them up in the paper if you like. The important thing is that what we get is something like this. So Alice's perspectival states and perspectival unitaries give a time evolution corresponding to this kind of circuit. So her clock just goes through, and when it reads 4, she applies her unitary in the middle, and Bob's unitary, depending on the value of the control, is either applied before or after she applies her own. And we get the same for Bob. So because the switch scenario is symmetric, you just have to swap indices UA, UB, and 0 and 1 on the control. And if you remember, these are exactly the perspectival circuits that I gave you when I talked about the causal reference frames. So the difference is now that I have this time information that tells me how each of these agents experiences time inside this non-causal process. Good. We also showed in the paper that something like this can be done for any type of coherent control of causal order in a general protocol that is, well, lengthy, but the main idea is really pretty much exactly what I just told you about the switch. So a process that implements general coherent control of causal order looks like this. I have my control reading values k from in some range, and for each k, I have a different process g tilde applied, where these g tilde are now causal processes, so something like this. These circuits with slots, of course not just two parties, but n now. And for at least two of the case, the ordering in which the agents plug in their operations in these g tilde are different. Right? So then I get indefinite causal order because I have some scenario where I cannot tell which agent acts before the other. If I have a superposition of two such pure causal processes with different orderings. And what we showed is that you can always do something like this, as I did for the switch. So you write down this Page-Wootters state, where there is at first a desynchronization step, where according on the value of the control, you initiate different orderings of the clock. Then there is this application part, where all the clocks actually tick in a synchronized way, and the agent just, well, and then these unitaries are applied, either the V of the process in between that you see, or the UX of the different agents. Always according to K in order to build up this causal process GK tilde. And at the end, you have this resynchronization step where you again use the control value in order to reverse basically what you did in the desynchronization to end up with all the clocks reading the same value again, and then you can perform your final tick that you wanted. And this general protocol that we wrote down in the paper works for any process of that kind, meaning any type of coherent control of causal order. Now, last but not least, another process which is problematic in our framework. Well, we call it the Lugano process. It was proposed by some members in the audience. This is a three-party process that is pure, non-causal, and not coherent. An example of coherent control of causal order, in particular for those who are familiar with quantum processes, can violate causal inequalities. So when applied to a state phi, it looks like this, where these P's are orthogonal projectors that sum up to the identity. So that the agent's operations acquire an X, sigma X or not, depending on which subspace you look at. And this process has, well, what I call a potential problem with our affine linearity requirement. In the following sense. First, if you look at the causal reference frame decomposition, which was given in the original causal reference frame paper, for this process it looks like this. For A, as an example, like it's the same for all the agents, you just permute them. But this can very decidedly not be the perspectival circuit that we recover from a global Page-Wootters state, because these gates here in the causal past of Alice do not depend are not linear or constant in the operations B and UC, right? So you can, if you insist that this is the perspective of an agent, you cannot think of three of these perspectives to come from a global Page-Wootters state. That is basically one result that you can obtain from our framework. Yeah, sorry. Moreover, if you just try to write down a Page-Wootters state anyways that is in accordance with our ideas, you run into what we call the resynchronization problem. So you can start off with using these projectors on the subspaces to again initiate different clock orderings, right? So you have potentially different orders that you can then implement. And then conditioned on these different orderings, you can implement these terms that once you combine them, would actually give you your G of UA, UB, UC. However, they appear in your state like this with 4 now orthogonal clock states that if you want to write down more terms, you would now have to map to 1 clock state again. And since you don't have a control, like in the example of coherent control of causal order, what you would have to do is use the system states to conditionally rotate them, right? But for these system states, you see that all the agency unitaries have been applied already. So if you now use them as a control, you will have to, again, introduce a dependence on these unitaries, which, when you write them in a state, will give you, again, a non-constant or linear dependence in the perspectival unitaries. And this is a problem. So basically, what I'm saying is that everything we could come up with for the Lugano process is incompatible with our framework. However, neither the causal reference frame decomposition nor our ideas of how to write down Page-Wootters states are the only ways to do this. So we could not completely rule out that there is not a smarter way that we haven't discovered yet, that you could actually write down a Page-Wootters state that gives you, as desired, the implementation of these processes, some nice perspectives, and fulfills all the other criteria as well. And with that, I say thank you.
Hey, yeah, thanks for this really nice talk. So this normalization operator that you introduce.
I knew you would ask me about that, but yes, go ahead.
So you know, what you were calling the global Page-Wootters state, sometimes called the physical state. This,
yeah.
You know, this is defined on one Hilbert space, and then you have these perspectival states which correspond to a different Hilbert space. Is there not could this normalization operator be understood as a change in the inner product?
Yes,
on that second Hilbert space?
Yeah, good question. So this is where an important difference between the continuous clock case and the discrete clock case comes in, right? For the continuous clocks, you automatically have what you said. So if you look at the conditional states there, you automatically end up with something that is not normalizable. So you need to redefine the inner product for the perspective. Yes, exactly, a change of measure when you and you include this in your inner product redefinition. For these finite dimensional clocks, however, you can project them out and have something that is perfectly normalizable in the state. So you don't need this change of inner product, and you usually wouldn't do it. But then, of course, you have these normalization issues sometimes. And therefore, we introduce these normalization operators where you basically can plug in by hand a renormalization every time you need it.
But it's not. Is it depend? If it's an operator, it's not dependent on the state, right? That state dependence is like within the definition of the operator. Have I understood that correctly? You don't need to like choose a different operator for different circumstances.
No, but yes, no, you don't need to choose, but for different times. So yes, it's not in that way state dependent, but sometimes what I'm saying is that sometimes you might need this factor, and sometimes you don't when you run through the perspectival states of each.
Right, and in the latter case, including the operator then would give you a non-normalized state. Is that right?
What not if you leave away that you get a non-normalized state. Yes. If you don't do the normalization operator, or what was your question? Sorry.
But you were saying sometimes it ends up being normalized anyway, and sometimes
yes.
you need to normalize it. But but with the definition, I don't know what the form of the operator is. If you include it in the states where you don't need normalization, do you then take what would previously have been a normalized state to a non-normalized state? Is that right?
I mean, maybe you could include it in the definition, but you would have to be. I mean, it would have to be very tailored every time. But I guess that's probably the same for the continuous case. I'm not that familiar with doing these redefinitions. So I guess you could do it like that as well. But it's, I mean, okay, I know the normalization operators seem artificial, but so does a redefinition of an inner product if I really don't need it.
Yeah.
So, yeah.
Thank you.
You're welcome. Online? Okay. You read it?
Yes. So actually, you can also unmute yourself and you can tell the online audience to.
Where are the online people?
So you can just tell them to unmute themselves and so you can see the chat.
All right. How did you model time? Time Hilbert space. The ticking, well, it's just a finite dimensional clock space, and the ticks are basically taking state 0 to 1 to 2 to 3 up to t. I mean, I completely agree that this is a terrible model for an actual clock, but it was just, it was really just there to, I mean, many of those clocks are terrible. So there is a whole area of research to look at better clocks and potentially interacting clocks and stuff like this. So we just wanted to include something that you could reasonably call, well, it's more a timekeeping system, right? Some system that keeps track of what's happening. In that sense, a clock, and in absolutely no other sense. That's it, right? Yeah. Continue with the...
When you say that you consider general coherence.
Yes. 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 I mean, the switch is one example. A coherent control. The switch is basically the maximally non-causal thing in the sense that for each k you really have different orders. So, and if the k runs through n values, so for every k you really have a different ordering. You can have something way less dramatic, where you have the same order for most of the case, but you have an inverted order or something like this.
Yeah, what I was wondering about is that you could have.
No, you mean basically an adaptive causal order where we have not looked at this, so we really just looked at the... we haven't looked at it, but that would be indeed very interesting. I'll have to look at it, yes. Thanks for the comment.
Yeah, thanks for the talk. That was this working. Yeah, that was really nice. So my question is about it relates to an information theoretic notion of causal structure. So a notion of causal structure that has to do with the possibilities of signaling between agents.
Yes.
Now, a common approach to defining such an information theoretic notion of causal structure is to look at the signaling relations in a channel or in a process matrix. So my question is, given one of these Page-Wootters models, should the information theoretic causal structure be defined in terms of the emerging process matrix, or should it perhaps instead be defined directly in terms of the history state? Or should it be defined in a different way entirely?
That is a good question. I mean, okay, so, which is not a satisfying answer to your question, but what our framework does is that if you say your causal structure is defined by the process, what this does is it tells you whether this process is compatible with this idea of a global Page-Wootters state at all. And I mean, I find it kind of interesting that this Lugano process, at least as far as we can tell, does not seem compatible with it. Whether you should define causal structure based on something else entirely, I mean, maybe. So I would say if the Lugano process violates causal inequalities, right? So if we ever observe that, then yes, then this tells you that you should define it differently, because our framework seemingly rules, or well, at least makes this process highly problematic, and if we observe it in nature, then this is not the way to do it, right? I don't have a final opinion on that, how to define causal structure, but yeah, I mean, and our framework is also incapable of answering that. But yes, I mean, it really depends on what you can then actually observe, right? I mean, you can write down a couple of things. I mean, what would be cool if you write it, if your definition of causal structure gives you an indication as to whether or how you can actually implement and observe these non-causal processes. According to this, I would then pick my definition, not based on what I just write down.
Cool, thank you.
Okay, so we have now a coffee break, and we will meet again here in 45 minutes. 10:45.
Thank you.